Folks, this is the part 2 of the third topic of chapter 9. We will focus on standard enthalpy of formation. Let's talk about some important terms. First one, standard states. Standard states means 1 atmospheric pressure, 25 degrees Celsius, and if you are talking about the chemical reactions involving solutions, then the concentration of the solution has to be 1 mole per liter. Second, standard enthalpy change. Okay, we use delta H reaction with this tiny circle to represent the standard enthalpy change. What does it mean? It means the change of the enthalpy at standard states. Well, we just discussed what the standard states are. Okay, this is the standard enthalpy change. Now the third one, standard enthalpy of formation. We use delta HF0 to represent this term. F represents formation, and this tiny circle here represents the standard states. All right. Now let's take a look at the details of the standard enthalpy of formation. The change in enthalpy when 1 mole of the compound forms from its constituent elements at standard states. It's quite long, but let's use this example to demonstrate to show you how we define standard enthalpy of formation. If you are talking about delta HF0 for methane gas, CH4, then according to the definition here, that's going to be the change of the enthalpy when 1 mole of the methane gas is synthesized. Right here, the coefficient is 1. So in this equation, okay, first condition is satisfied. You have 1 mole of the methane CH4 synthesized from this reaction. Now, second condition forms from its constituent elements. Okay, well, you have 2 elements in CH4, carbon and hydrogen. So in order to find out the standard enthalpy of the formation for CH4, you have to do the synthesis by using carbon and hydrogen elements directly. Okay, so that's what the second condition means, elements. Now the third condition is standard states. You have to perform this synthesis at the standard conditions right here. All right, when all 3 conditions get satisfied, then the enthalpy change that is associated with this reaction is the delta HF0 for methane gas. Well, here the enthalpy change for this reaction is negative 74.6 kilojoule per mole. All right, so this is the standard enthalpy of the formation for methane gas. All right, okay, this is how we define standard enthalpy of formation. Now the second thing is, for a pure element in its standard state, delta HF0 equals to 0. For instance, delta HF0 for carbon would be 0. For delta HF0 for hydrogen, it's going to be 0. So for those most stable elements, the enthalpy, standard enthalpy of the formation for them would be 0, because you cannot synthesize those most stable elements by something else. Okay, so that is the how the standard enthalpy of the formation. Now, people with scientists have already performed a bunch of experiments to find out the standard enthalpy of formation for some common compounds here. Okay, so this table shows you part of the database. And in appendix, I think it's number 1, it shows you a much much larger database of standard enthalpy of the formation. What does that mean for us? Well, if you recall, in the previous videos, we talked about how we identify the enthalpy change of a reaction, right? So in theory, you should perform the chemical reaction in the bomb calorimeter and find out the enthalpy change associated with this particular reaction. So can we make it easier for us to do? Well, that is where that standard enthalpy of the formation can help us. Okay, let's take a look at this this example. Okay, let's see. Use standard enthalpy of the formation to calculate delta H reaction for this reaction. Well, like I said, that in theory, you can perform this reaction in your lab to find out the delta H reaction experimentally. Okay, but here I want to show you that by using the data from this table, we can just do calculation to find out the delta H reaction that is associated with this reaction. In other words, instead of doing experiments, you can just do calculation to find out the delta H reaction for a particular reaction. Okay, so let's see how we do this reaction. Before we start the calculation, let me tell you how we use standard enthalpy of the formation to find out the delta H reaction. Okay, here this is a general equation. I'll write it on top because it's quite important. Delta H reaction at standard conditions, that equals to sigma N P delta H F0 products minus sigma NR delta H F0 reactants. I'll write it here, okay? All right, now let me explain it. Well, here the first thing is sigma. Sigma means sum, okay? So in other words, you have to consider both products when you consider this first part, okay? NP, P represents product. N here means the coefficient of each product. Now, delta HF0 product means that the standard enthalpy of the formation for each product. For this case, it's going to be carbon dioxide and water. Minus, okay, this is the first part, and then this is the second part. Between the two parts, it's a minus sign. Okay. Now, the second part, sigma, again, sum. Now, NR, R represents reactant. N means the coefficient of the reactants. The delta HF0 for reactants means the standard enthalpy of the formation for reactants. For this particular case, it's methanol and oxygen. Okay, so please make sure you understand the meaning of this equation, okay, because it's very important for you to perform the calculation for chemical reactions. And if you need to take a Chem 2, then you will see this equation again in Chem 2. Okay, so a good understanding here will help you later on when you study the thermodynamics chapter in Chem 2. All right, now let's set up the equation and do the calculation. All right, now according to the equation here, we need to consider products first. Well, you have two products, carbon dioxide and water. Pay attention to the state, okay? Because if you take a closer look, water in gas state is associated with the enthalpy of negative 241.8 kilojoule per mole, and water in liquid state is associated with negative 285.8 kilojoule per mole. So be careful about the states, okay? Of course, the data, those standard enthalpies of formation will be given in your test. So you don't need to memorize them. You just need to know how to use them, okay? All right, now it's time for us to start. For products, all right, the first product, let's see, carbon dioxide. You have 2 mole of carbon dioxide, so this is the first MP, okay? 2 more carbon dioxide times, well, for carbon dioxide, you have right here, okay, right here. I'll use red color to highlight carbon dioxide right here, okay? All right, now that is negative 393.5 kilojoule per mole. This is the first product. Now between the second product is water in gas phase. All right, here sigma means sum. Therefore, it should be a plus sign. Now you have 4 mole of water, so 4 mole of water times for water in gas phase. Okay, again, I'll use red color. It's going to be associated with the standard enthalpy of the formation of negative 241.8. Therefore, it's going to be negative 241.8 kilojoule per mole. All right, this is the first part. We finished this. Now the second part would be about the reactants. Of course, between the two parts, it's minus. Okay, minus. Now the two reactants. First one, methanol. The methanol is right here. Okay, and you have 2 mole methanol times negative 238.6 kilojoule per mole, and plus. Now second reactant, oxygen. Well, if you take a look at the oxygen, where is oxygen? It's right here. It's 0. Well, this makes sense, right? Because when we talk about O2, it's a free element. It's the most stable form of the element oxygen. Therefore, according to the discussion we had on the previous slide, the delta HF0 for oxygen O2 would be 0. All right? Still, let me write that down. You have 3 mole O2, but of course, you multiply 0 kilojoule per mole in this case. All right, this is the whole equation. It's quite long and a lot of numbers get involved, so just be careful. All right, now let's do the calculation carefully. Well, this part here, I'll write more steps here so you can confirm your calculation. So that means that's in the first bracket. The first one is negative 787.0 kilojoule. All right, this is from this part. Now the second part right here, okay, plus negative 967.2 kilojoule. All right, these are the two products. Okay, minus, I'll write it down here. The second part, that's going to be from this one. Okay, of course this one would be 0, so I'll just write this one here. That's going to be negative 477.2 kilojoule. Okay, pay attention to the units. Well, here the mole has been cancelled. Why don't I'll go ahead and just write, just cancel them. Okay, cancel. All right, so that's why we have kilojoule only when we got here. All right, now when you have these two together, that will be negative 1754.2 kilojoule. Now you have negative sign here, they cancel each other out, so that means plus 477.2 kilojoule. And then the final answer should be negative 1277.0 kilojoule, 1 decimal place, because both of them have 1 decimal place. All right, so as you can see that instead of doing chemical reaction to find out the delta H reaction at standard states, we can just use the standard enthalpy of the formation of those reactants and products to find out the delta H reaction at standard states for this reaction. Okay, so it's much easier and it's much faster. All right, we'll do more practice.